Hello, and welcome to Cloudy with a Chance of Chaos. My name is Christina Yakomin, and I am the lead engineer on Vanguard's Chaos and Resilience Engineering team. Before I begin, if you want to reach out to me about any of the information that you see in this presentation, feel free to do so on LinkedIn. You can find me pretty easily, Christina Yakomin, or on Twitter at SREcristina. In this presentation, we are going to talk about what chaos engineering is, why we do it, and how we implemented our own custom tool for it over the past year and a half. I wish I could be there in person to do this with all of you today, but hopefully you appreciate my feeble attempt at a festive backdrop here while we are all remote and working from home. Let's go ahead and get started. What is chaos engineering? I'm going to define it for you, but first I thought I would share some of the attempts that I have heard to define chaos engineering from folks who aren't actually quite sure what it is. The first one that I hear really often is breaking things on purpose. And while it is true that at its core, chaos engineering involves fault injection, this one is definitely a bit of an oversimplification, and that's probably putting it lightly. There's no one at Vanguard who is going to come give me a pat on the back for breaking our production systems, that's for sure. How about this one? I know it's something that Netflix does, but we could never do that here, wherever your respective here may be. And yes, the practice of chaos engineering did originate at Netflix. That part is true. But just because we're not a tech company doesn't mean that we can't leverage chaos engineering. Even in a highly regulated industry, which at Vanguard we know something about, we absolutely can run chaos experiments. In fact, we already have. This one makes me laugh. Isn't that just a fancy name for performance testing? It's another buzzword. And sure, sending a ton of load at an application is one form of stress. I would say that the two go hand in hand. But chaos engineering encompasses so many more faults than just significant load. And it's a whole lot more than just a buzzword. How about this last one? What the heck is that? It's okay if this is still your level of understanding of chaos engineering. Honestly, when I share my job title with other pros in the industry, sometimes I get that confused, quizzical response. When I have to explain what chaos engineering is, I typically say it's pretty synonymous with resilience testing. And that definition is a lot more palatable to my product owners and key stakeholders sometimes too, compared to what chaos might imply. But for the true definition, I'm going to borrow from principlesofchaos.org, which is a really great resource if you're just getting started with chaos engineering and want to learn more. I highly recommend checking it out. They define it as the discipline of experimenting on a distributed system in order to build confidence in that system's capability to withstand turbulent conditions in production. I think that sums it up really well. But as nice as these words are, sometimes it can be most helpful to see it applied, to see it in action. And while I'm not going to do a live demo on Vanguard's websites today, let's suspend our disbelief for a moment. Let's pretend that I don't work at Vanguard at all. Let's pretend I own an e-commerce company called Shopping Website and that we've got a super cool line of apparel that we are trying to sell. Clearly, branding, not necessarily my strong suit. It is probably pretty obvious at this point that I don't work in PR or marketing, but that's okay, just roll with it. We've got the super cool hat on this page that looks like your typical e-commerce webpage. Product image, product name, the price, some shipping, reviews, the ability to add it to the cart. Obviously, in this fictional example, I've already added something to my cart, who knows what. And then some recommendations at the bottom, things you might also like, which in this case appear to be some other items from the same line. So, if we assume that there is a pretty complex distributed system powering this page, we might be able to come up with some ideas for what those things are. You've got the recommendations engine, you've got the shipping calculation, you've got something retrieving how many items are currently in my cart, the ability to add something new to my cart. All of those might be independent APIs running on different systems. So, if we're going to chaos test this site, the first thing that we'll want to do is talk about the different ways that such a complex system could fail. This is exactly how we do it at Vanguard. We sit down usually with the architecture diagram of the application that we're talking about, and we identify all the different failure modes. The technique is called a failure modes and effects analysis. It's borrowed from the physical engineering disciplines like mechanical engineering and has since been applied to IT resilience engineering. We've found it really effective as a method of hypothesis definition. So, an example here would be all right, what happens if the recommendations engine is unavailable? Planned maintenance, or simply a bug has been introduced and now it's returning 500 errors. Or maybe it's really slowed down, it's super latent. Are we just going to explode? Is the page going to say server error to the client? Is it going to inherit the response time of the recommendations engine and just have a loading indicator on the screen forever? Well, we hope not, right? Because the core functionality of this page is the customer's ability to add the super cool hat to their cart and go ahead and check out so that I, the owner of shopping website, can make my sale. That's the most important thing. So we trust our developers. We know that they've built in some really great graceful degradation on this page. They've made it so that if the recommendations engine is unavailable for whatever reason, you're not going to explode. You're not going to wait forever. Instead, you'd expect to see something more like this. If I'm new to the website, I might not even realize that anything is wrong with this picture. To validate and verify that everything is working the way that we expect with this graceful degradation, we could run a chaos experiment. We could inject a fault into the recommendations engine and observe it and make sure that everything looks exactly the way that we think it does. Because no matter how we've built it, even if we've got some integration tests, with a system this complex, there might be unintended consequences. So it's always helpful to get that extra level of verification. One more example from this page might be the reviews. I know I personally always like to check the reviews before I buy something. This super cool hat, obviously amazing reviews, 5 stars, 207 people like it. I'm totally going to buy this, but not everyone is like that. Some people will go ahead and make the purchase anyway. And maybe the fictional scenario we can talk about here is someone came in and bought the super cool hat already on Black Friday. They got it, they love it. Now they want to buy 5 more so that every single one of their family members gets a super cool hat for the holidays. Maybe. So they don't need the reviews, right? They're already ready to make their purchase. They're here on a mission. They know what they want to do. I want to make that sale. But if the database where we store all of the reviews is unreachable, we can say in this scenario, maybe it ran out of threads. That would suck. Then, how do we want the user experience to look? What's our expectation? Well, based on what the developers think they've built, the expectation is that the page looks like this. We can test that with a chaos experiment. We can make that database unavailable and ensure that by the time the entire complex system has worked together, the result is still going to allow the client to add the hat to their cart, check out, and make that sale. So hopefully this little shopping website illustration has set the context for you of what chaos engineering is, what it can look like. This is not comprehensive, right? It's not all going to be web-based. It's not all going to result in something interesting on the front end. But this was the most illustrative way that I could get the point across of what chaos engineering can look like. With all of that context now being set, let's talk about why this chaos engineering is so valuable. As we're migrating to the cloud, we're becoming more and more comfortable with treating our servers as cattle rather than as pets, as that old saying goes. And that's a really good thing because when we're using commodity compute in the cloud, infrastructure fails all the time. We're either relying on resilience mechanisms from our cloud provider, something like auto scaling, or custom automation, like that graceful degradation that the engineers built in the shopping website example, to ensure that we can self heal whenever these faults occur. We should be testing those things. The last thing that you want is for a production incident to be the time when you realize some of those resilience mechanisms that you've either built or configured don't quite work exactly the way that you expected them to. You don't have a comprehensive mental model of your most complex systems. So sometimes there are unintended consequences. Chaos engineering can bring some of those to light. And chaos engineering is great for the human aspects of your systems too. Think about your incident responders and your engineers on call. You can use chaos engineering to train these people to practice reacting to failures. You can inject a fault to which the system maybe isn't so resilient and make sure that the appropriate alerts are firing and that recipients know what to do once they're notified. I've personally seen this in action, onboarding new team members to an on call rotation, and I found it to be incredibly effective in building their own confidence to take on that on call rotation for the first time. They always feel a little bit better knowing that they've had time to navigate the run books and the dashboards during the workday with some help if they need it, rather than having to do that for the first time at 3 a.m. when their pager goes off, because that's no fun for anyone. With pretty much that exact pitch, a grassroots group of engineers at Vanguard was able to convince the senior leadership that we should fund a very small team to make chaos engineering happen. But it was small. They had one full-time engineer and one intern, and that was it. So the first question they had to ask themselves for implementation was this one: would they build something or buy something? With very little funding, naturally the first place they looked was the open source community, hoping that they'd find one of the many libraries out there met their needs. Unfortunately, it didn't quite work out that way. At Vanguard, there are rigorous automated security controls that would have been a lot of upfront work to integrate with. Many of these libraries assume that developers can execute a command via a CLI on their desktop that can target any server on the network, or that they can SSH out to these servers and execute commands with root permissions. At Vanguard, that is simply not the case, probably for obvious reasons. So we ruled that out and started looking at some more advanced vendor products instead. But there's not too many of these on the market, and because of that, they're very, very expensive. Yes, they had some better out-of-the-box security integrations, but since we didn't have enterprise-wide buy-in for chaos experimentation yet, no one was willing to foot the bill for such a large purchase. So it became pretty clear pretty quickly that we had no other option than to forge our own path and build and deliver our own lean MVP and iterate from there, demonstrating our value every single step of the way. That's how we ended up building the climate of chaos, because what is more chaotic than weather? Over the past year and a half, we built this Climate Control Center web application, which allows engineers at Vanguard to run experiments with weather-themed names like tornado and cyclone. We call these phenomena. These phenomena represent different types of faults that can be injected into a system across a variety of the platforms that we have in use at our company, including EC2, ECS, and RDS, just to name a few. When we first released the tool for internal use, a few months into our development cycle, we only had a couple of available options for experiments. But since then, we've grown to support 16 different types of fault injections, and that number is increasing all the time. If a user selects Chaos Flash Flood for this example, that's an experiment that increases CPU utilization on an instance or a task for a period of time. That user will then be prompted to provide just a few inputs about their infrastructure, like the account where it's running, the task IDs, the region, things like that. And then they can run their experiment at the click of a button. It's really that simple. So I bet you're probably wondering at this point how this all works, how we built this, how we put it together. And I'm going to explain that. The way I'm going to do that is by talking you through the 4 guiding principles that we had in mind while we were building the climate of chaos. They are serverless, easy adoption, defined guardrails, and integrated reporting. I'll talk about each one of the 4 over the next several slides. And we'll start, of course, with serverless architecture because I think that's probably going to be the one that's most interesting to everyone here. How did we actually build it? What are the components in play? Serverless, well, that was important to us for a couple of reasons. First, high availability with low operational complexity, and then also really low cost. Low cost is going to come into play a ton here. The funding was small. So I'm going to repeatedly talk about the concept of a consumption-based pricing model. I want to define that up front before I continue to make sure we're all on the same page. When I say consumption-based pricing, what I really mean is that you're only paying for what you use, meaning we're only incurring a cost when someone is running a chaos experiment. Actually, the only counterexample to this within our architecture is the ECS web application. We're using the Fargate option for ECS, and we've got a task provision that's running 24/7, even if no one is accessing the tool. So we're always paying for just a little bit of compute. But we are leveraging something like auto scaling so that we are able to add additional tasks when demand increases so that we're not constantly over provisioned. But there's always something running. So not truly consumption based here. But it is pretty close to that serverless because of Fargate. It takes the operational complexity out of container provisioning and lets Amazon handle that for us. The VMs are not our concern. Our web app is Python based and it uses the Flask framework. This helps us to limit the number of different programming languages that our team needs to know and understand, which has been a huge help when onboarding new team members. At one point, we had major workloads in Node.js and Java and Python, not to mention all of those different AWS resources. And that's a lot of breadth of expertise for a new team member to get up to speed on, especially when you're hiring junior developers. We've been lucky to have some rock star developers on this team, but even for the experts, it's nice to limit the amount of context switching between languages that we need to do. And the rest of our application is also in Python. That backend experiment execution functionality is all built out with AWS Lambda, the serverless compute that I'm sure most of you are familiar with at this point, and AWS step functions. Step functions is a workflow management tool that pairs really nicely to string together all of our Lambda functions. It allows us to introduce wait states into our system without having to pay for that time that's spent idle. Both Lambda and step functions operate on a truly consumption-based pricing model. So we can keep our costs super low, increasing steadily with the utilization of our platform. For storage, this will probably come as no surprise to the folks who are familiar with the storage options available at AWS. We're using AWS DynamoDB. Dynamo is an interesting one. It has 2 distinct pricing models, provisioned throughput and on-demand capacity. We started with provisioned throughput at really, really low numbers considering our low traffic, but we've since switched to on-demand capacity, which makes the expense for our Dynamo workload truly consumption-based. While we do pay more per consumed capacity unit, We end up paying significantly less overall due to the sporadic and bursty nature of the traffic on our platform. Usage is currently relatively low, especially outside of business hours, and it's pretty unpredictable too. We never know when one of our internal clients is going to pick up the tool and try to run a chaos experiment. So when I say significantly less expensive, we're talking the difference between hundreds of dollars per month and like tens of cents per month. This was huge for us. Finally, the last piece of this puzzle is CloudWatch, specifically CloudWatch events rules. We're using these to support scheduling of experiments for our clients on a cron expression, as well as generating synthetic traffic through our step functions throughout the day, allowing us to quickly detect any new issues whenever they arise, whether that's a change that we've introduced into the system or something else in our environment or our ecosystem that has changed that affects our ability to run experiments. Again, words are great, but sometimes pictures are better. So I have a couple of simplified architecture diagrams that we can talk through here to hopefully illustrate how all of those pieces are working together. There's the ECS web app running in a centralized operations account. That's the front end that the client is able to access and see. It runs with a cross-account IAM role, which grants it permissions to execute step functions workflows in whichever AWS account the client is targeting. So wherever their infrastructure resides, that's where the step functions reside. This is a little sneak peek into our integrated reporting principle, which is the fourth one. But we actually start by enabling a synthetic probe that's going to send some traffic to the targeted application. Then we wait for a while. We establish the steady state, get a feel for how the application behaves under normal conditions. Then we inject the stimulus. That's going to look a little different depending on which experiment you're running, targeting EC2, ECS, RDS. In 2021, we'll be adding EKS. And then upon the completion of that experiment, we wait again. Then we disable the synthetic traffic, and we've got quite a bit of data there that we can observe to tell us what happened during the experiment. This architecture diagram is similar, but slightly different. That was an ad hoc experiment, someone coming into the web app and running a single experiment right then and there. But maybe they've now done that a couple of times and they're confident in the outcome. They want to now automate this and repeatedly verify this. So they're going to schedule the experiment to run on a weekly basis. They would go into our web app and manage a saved experiment, which we're storing information about in our DynamoDB table. We've got that DynamoDB table set up with DynamoDB streams enabled. So anytime a row is created, updated, or deleted, a Lambda function is triggered. That Lambda's job is to translate whatever has been put into the Dynamo table into a CloudWatch events rule and give it that cron schedule that it needs so that it can trigger on a regular basis and invoke the step functions workflow. This part looks exactly the same as what you saw on the previous slide. But like I said, it's simplified. That's not all of the complexity that we actually have. This is, kind of. This is a real image taken out of the AWS console of our step functions workflow, but it doesn't even tell the full story. I know the text is pretty small here. Don't worry too much about the details, but you can certainly make out that row kind of toward the middle, maybe bottom third. That's all of the different experiments. So it'll pick one of those experiments based on the user inputs. Many of those states are actually nested state machines themselves. So if you were to click through in the AWS console, you can actually get to an entirely different state machine with steps of its own. Lots of complexity, very distributed, but really easily observable thanks to step functions. If something went wrong at any point in the workflow, instead of that lovely neon green that you see, you'd see red. We can easily see the path that the experiment took through our workflow and where something went wrong. At that step, we're able to see the input, the output and click through to the resource, whether that's a Lambda function or something else that is behind that state, find its logs, and see what might have gone wrong, which has made troubleshooting this platform super easy. Speaking of easy, let's move on from serverless architecture into easy adoption. We never wanted teams to have to submit tickets to us and wait before they would run chaos experiments. As a really small team, that wasn't going to work. So we've given all IT teams access to our tool so they can self-service their experimentation. This is a much more scalable model for our small development team and ensures that our bandwidth will not ever become a bottleneck that prevents the broader adoption of our tool. This one might sound too good to be true, but I promise it was actually one of the most important tenets that we set for ourselves when we were initially building out the climate of chaos. There are no code changes needed to get started. We know that these engineering teams are already so busy working on delivering critical business functionality for the products that they support. If the barrier of entry was too high to start using our tool, it would hinder the adoption of chaos engineering overall at Vanguard. So, the most that a team needs to do to get started, the most, is make a couple of small configuration changes. Really small. We're talking about 5 lines in total. And in many cases, teams just need to add one tag to their AWS resources. Finally, documentation. And I know I've never met an engineer who said that documentation was their favorite part of their job, and my team is no exception. But thorough, approachable documentation has been so critical to our success. By creating easy to understand user guides for our clients to pair with our self service tool, we've been able to spend a lot less time providing support and onboarding new clients and more time doing the work that we really enjoy, which, of course, as engineers, is developing new features. I have to mention it. So, I just told you that we gave access to all of IT to use our tool. So we're going to need some defined guardrails on that. The first way that we minimize blast radius is prioritizing single target experiments so that teams can go ahead and get started right away without needing to chase down approvals from dozens of key stakeholders. When I say single target experiment, what I'm referring to is experiments that are targeting a single EC2 instance or a specific ECS cluster, rather than modifying a shared security group or taking out an AWS region for an entire AWS account, because you probably see how that could have some broad reaching impacts that we don't necessarily want to mess around with. For permissions, we're leveraging tagging native to AWS. We conditionally grant IAM permissions to our tool based on the presence of this tag. This prevents fault injection from accidentally targeting infrastructure that hasn't yet opted into experimentation. So the way this works is if I have an application that runs on an autoscaling group of EC2s, and you have an application that also runs on an autoscaling group of EC2s in the same AWS account, I'm super jazzed about chaos engineering. I'm ready to go. I've added a tag to my application. All the instances have that tag. I deployed it via CloudFormation. I go into the AWS console. I'm looking at the Climate Control Center. I'm flipping back and forth between the two tabs. And yeah, I copy your instance ID instead of mine by mistake and paste that into the Climate Control Center. Uh-oh, right? Now I'm going to run an experiment against your infrastructure instead of mine. Well, actually, no, I'm not, because by the time that the Climate Control Center gets to that step where it would inject the fault, it's going to receive an access denied from AWS trying to make modifications to your infrastructure because it doesn't have permissions. You haven't added that tag to your resources, so they are safe. You are protected from my mistake. I'll notice something went wrong. Thank the fantastic developers on the Chaos team for thinking ahead, and I'll go copy the correct instance ID and I will try again. This might be controversial. I'm going to talk about it a little bit now. I'm going to circle back around to it at the end of the presentation, I promise. We're sticking to non-production while we're proving this out. Look, at Vanguard, There are a lot of security architecture reviews that you need to go through before you can get any new system into production. And rightfully so. At Vanguard, the most important thing is protecting people's money. And we needed to develop this tool quickly and demonstrate value quickly. And we were going to iterate. So for our MVP, we stuck to non-prod. That got our time to market down significantly. It got the tool in the hands of clients faster, and we are seeing it provide some value. So it's not out of the picture forever. This is just for now. Again, I promise I'll talk about this again at the end of the presentation. Don't get too mad at me just yet. The last guiding principle is integrated reporting. Fault injection, it's only useful if you can see the results. If you can't see how the system is behaving, your chaos experiment isn't going to do you any good. That's why we provide functionality within our tool that allows users to set up steady state probes. You saw this in my architecture diagram earlier. We call this aspect of our tool radar, of course, in keeping with our weather theme. The probes send light but consistent traffic to an application's REST endpoint throughout the duration of an experiment. And it uses structured logging to provide insights about how the system's behavior is changing, if at all. Then we created dashboards in Splunk with queries based on Radar's structured logs, so teams don't need to go searching for their experiment results. Once they execute that experiment and click the button, a dashboard URL is provided to them that pre-populates several dashboard parameters based on the inputs they provided to the Climate Control Center. The link takes them directly to their results, presented in a way that is really easy to interpret with no need to write any custom queries. They can even compare the results of this experiment against past experiments run on the same target. It's important to note here that our goal was not to become a round-the-clock synthetic monitoring tool, nor were we trying to enable load testing. We're not the observability team or the performance testing team, we're the chaos team. Radar sends just enough traffic in the context of a chaos experiment to provide data about the system behavior for analysis. And it is our hope and expectation that some teams that use our tool aren't going to need this. Their level of maturity in the observability space will probably outclass what we've built here. And we think that's awesome. But for those teams that aren't quite there yet, we don't want to leave them behind. So we're providing the bare minimum that they need to be ready to start running chaos experiments on their applications while they're still on that maturity journey with observability. So that's pretty much everything that we've accomplished in the past year and a half, boiled down to about 30 minutes. Now let's talk about what's next for the team. Of course, we're going to continue to develop new phenomena. I already mentioned this, but next year we're going to start trying to support AWS EKS as a target for fault injection, as teams at Vanguard start to look at that platform as a place to run their Kubernetes workloads in the cloud. So that's on deck for 2021. This one's really exciting to me. We're also going to focus on coaching to encourage broader adoption. In the past year, we've gotten a lot of these self-starters and early adopters on board, but we're going to start dedicating some more cycles to educating the product teams at Vanguard about the value of chaos engineering and make our sales pitch tell the good news stories from the past year to get the rest of them on board as our clients. In some cases, we'll even help them analyze their architectures to identify appropriate targets for fault injection with those failure modes and effects analyses. We do have some plans to introduce some more complex tools that are going to require minor code changes. This is for those advanced faults that we can't quite introduce without the code changes. So this will be targeted at our power users who have already been using and loving the existing Climate of Chaos functionality and are ready to dive even deeper. Last but not least, more advanced automation and scheduling. I mentioned cron expressions in that context of the CloudWatch event rules earlier. I think our next level of maturity in this space is rather than running an experiment daily or weekly or monthly, we run that experiment anytime a change has been made. I don't know what that implementation will look like just yet. Maybe we automatically detect that a new release has been deployed to the environment and we run a suite of saved experiments, or maybe it is a post-deploy task that hooks directly into our CI/CD pipeline. But I'm excited to see us mature in that space and give some faster feedback based on changes. Now, there are two important things that you don't see here on this list that I also want to address. The first, as I promised, is bringing our chaos testing functionality to production. At this point, the practice of chaos engineering just isn't mature enough at Vanguard to warrant the effort. But it is on our long term roadmap as a team. We see ourselves getting to that point eventually, inevitably, because testing in production is the most effective way to understand how your production systems behave, no matter how production like your non production systems are. For now, we're going to continue educating teams on chaos engineering concepts and fundamentals, and we will deliver a production ready tool suite further down the road just in time for teams to be ready to use it. The second thing that you don't see here is open sourcing the tool. This one is on my personal wish list. I have always wanted to make this tool available open source so that others working at companies with that same rigorous security are able to take advantage of what we've built. And there is still a small chance that we'll begin the process of open sourcing some aspects of the climate of chaos in 2021. But if we're going to do that, we're going to need more buy in from our IT leadership teams first so that we can staff up to support that effort. So, if you liked what you saw in this presentation, which I so hope that you did, please feel free to send me your feedback. I'll share that internally with our IT leadership teams so that we can make an even stronger case for allocating additional resources to chaos engineering. It really would mean so much to me to hear from all of you and help me make that business case that everyone is so excited we have to open source this tool. With that, I want to say thank you so much for tuning in to Cloudy with a Chance of Chaos. Once again, my name is Christina Yakomin. You can find me on LinkedIn or on Twitter at SREcristina to send me your questions, your feedback, or I would love to connect to talk about how to make a grassroots effort at your companies turn this idea about chaos engineering into reality. I absolutely love talking about the journey that we've been on to get to this point, from being just a team of one engineer and an intern to now a team of 6 that intends to double in size next year to a team of 12. Chaos and resilience engineering has grown really organically at Vanguard, and I hope that you take away some new technical learning from this presentation, but also some inspiration to go make some changes at all of your organizations. With that, again, thank you so much, and I hope you enjoy the rest of your experience at SREcon.